I want you to drop something. Seriously, pick up whatever is next to you right now, your phone, your pen, a book, anything. Hold it out and drop it. It fell. Of course it fell. It always falls. Now, here's the question I want you to sit with. Why? Not what is the equation? Not what is the acceleration due to gravity? Not what is the gravitational constant? Why does that object fall toward the Earth at all? What is actually happening physically in the space between your hand and the floor that causes that object to accelerate downward? I have asked this question to physics teachers, to university students, to engineers. Most of them give me an equation. Not one of them gives me an answer. Because here is the truth that Richard Feynman stated plainly in a series of lectures that most people have never heard of. Nobody knows what gravity is. Not really. Not at the deepest level. Newton admitted it. Einstein reformulated it. And the greatest minds in physics today are still fighting over it. Today, we are going to find out exactly how much we do know, how much we do not, and why the honest answer to that question is one of the most extraordinary stories in all of science. G'day, and welcome back to Curious Physics AU, the channel where we take physics seriously enough to admit what we do not know, and find the beauty in that honesty. I am Abdullah, and today we are tackling gravity, the most familiar force in the universe, the one you have experienced every single second of your life, the one you studied in year 9, year 10, year 11, and possibly year 12. And yet, I am willing to bet you have never truly been taught what it is. Feynman had a set of lectures, less famous than his celebrated Caltech series, where he specifically wrestled with the nature of gravity, where he drew a sharp line between what physics can calculate and what physics actually understands. Today we are walking that line together, from Newton's apple in an English orchard, to Einstein's curved space-time, to gravitational waves rippling across a billion light-years of space, to the deepest unsolved problem in all of modern physics. Buckle up. This one goes deep. Let us start with Isaac Newton, 1687, the Principia Mathematica, one of the greatest scientific achievements in human history. Newton's law of universal gravitation states that every object with mass attracts every other object with mass. The force between them is proportional to the product of their masses and inversely proportional to the square of the distance between them. F equals G times M divided by R squared. Beautiful, precise, extraordinarily powerful. With this single equation, Newton could calculate the orbit of the moon, the trajectory of comets, the tides in Sydney Harbour, the motion of every planet in the solar system. For over 200 years, this equation was the most successful scientific formula ever written. But here is what Newton himself wrote, in his own words, about what the equation actually meant physically. He wrote, "I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses. Newton, the man who discovered gravity, openly admitted he had absolutely no idea what gravity actually was, or how it worked across empty space. How does the Earth reach across 150 million kilometers of empty space and pull on the sun? How does the sun know the Earth is there? What carries the gravitational influence?" Newton calculated gravity with breathtaking precision, but he never claimed to understand it. And here is the thing Feynman always emphasized. Knowing the equation is not the same as understanding the phenomenon. You can know that F equals mg tells you how fast something falls, but that tells you nothing about why it falls. Newton gave us the most powerful description of gravity in human history, and he was the first to admit it is only a description. The explanation was still 2 centuries away. Albert Einstein, 1915, The General Theory of Relativity. We covered Einstein's field equations in detail in a previous Curious Physics AU video, so today I want to focus specifically on what general relativity says about the nature of gravity, and what it says is radical. Gravity is not a force. Let me say that again because it deserves to land properly. Gravity, the thing that pulled your object to the floor just a moment ago, is not a force in the same sense that pushing a shopping trolley or kicking a footy is a force. Gravity is the curvature of space-time caused by the presence of mass and energy. Here is the key insight, Einstein's equivalence principle. Imagine you are in a lift, an elevator, somewhere in deep space, far from any planet or star. The lift is accelerating upward at 9.8 meters per second squared. You drop your phone inside that lift. It falls to the floor. Now, is that because of gravity or because of the lift's acceleration? You cannot tell. There is no experiment you can do inside that sealed lift that distinguishes between gravitational pull, downward, and upward acceleration. They are physically identical. Einstein took this observation, which seems almost trivially simple, and built an entire theory of gravity from it. If acceleration and gravity are identical, then gravity must be related to the geometry of spacetime itself, because acceleration in spacetime is a geometric concept. Think about it this way. Imagine two aeroplanes leaving Sydney Airport at the same time, one heading to Melbourne and one heading to Perth. Both fly in perfectly straight lines according to their instruments, no turns, no curves. Yet, if you watch from space, their paths curve toward each other slightly, because they are following the curved surface of the Earth. The straightest possible path on a curved surface is not a straight line in flat space. That is exactly what happens with gravity in Einstein's theory. Objects in free fall, like the International Space Station orbiting Earth, are not being pulled by a force. They are following the straightest possible path through curved spacetime, a path curved by the mass of the Earth. The apple does not fall because Earth pulls it. The apple falls because Earth curves the spacetime around it, and the apple follows that curve. That is Einstein's gravity, not a force reaching across space, a geometry, a shape, a curvature in the fabric of reality itself. Now, let us make the equivalence principle real, because it has consequences you experience every single day without realizing it. The equivalence principle means that being stationary in a gravitational field is physically equivalent to accelerating upward. Right now, sitting or standing wherever you are, you feel the floor or chair pushing up on you. That push is your normal force. It is what stops you from falling through the floor. But here is the Einsteinian perspective. You are not sitting still in a gravitational field. You are being accelerated upward by the floor at 9.8 meters per second squared, away from the natural freefall path that space-time curvature would otherwise send you on. The astronauts on the International Space Station, floating weightlessly, are actually in the more natural state. They are following the curved geometry of space-time freely, no forces acting on them at all. We, sitting on Earth's surface, are the ones experiencing a force, the normal force of the ground pushing us away from our natural free-fall trajectory. Weightlessness is the natural state in Einstein's universe. Weight, the feeling of gravity, is what you experience when something stops you from following space-time's curvature. Your chair is what causes you to feel gravity right now, not the Earth. Think about that next time you sit down. Einstein's general relativity made an extraordinary prediction in 1916, 1 year after he published the theory. When massive objects accelerate through space-time, they create ripples in the fabric of space-time itself, propagating outward at the speed of light, like ripples spreading across a pond when you throw a rock into it. Einstein called them gravitational waves, and then, almost immediately, he privately doubted they were real. He thought they might be a mathematical artifact, a quirk of the coordinate system used in the equations rather than a genuine physical phenomenon. He was wrong. On the 14th of September 2015, exactly 100 years after Einstein published General Relativity, the LIGO detector in the United States picked up a signal. Two black holes, each roughly 30 times the mass of our Sun, had been spiraling toward each other for billions of years, 1.3 billion light years away. In the final fraction of a second before they merged, they released more energy than all the stars in the observable universe combined, as gravitational waves. Those waves spread outward across a billion light years of space. They arrived at Earth, and they squeezed and stretched the LIGO detector, a 4-kilometer-long laser interferometer, by less than 1,000th the diameter of a proton. 1,000th of a proton. That is the most sensitive measurement in the history of human science. And here is the Australian connection that makes me genuinely proud. The Ausgrav Research Centre, based at Swinburne University in Melbourne and multiple Australian universities, plays a leading role in gravitational wave astronomy. Australian physicists and engineers helped develop the technology and analyse the data that detected these waves. When you hear about gravitational wave discoveries, Australian scientists are in that room. Gravity, detected not as a force, but as a wave in the geometry of spacetime itself. Einstein's most extraordinary prediction, confirmed 100 years later, with Australian hands on the instruments. Now, here is where Feynman enters the story in his own unique way. Feynman approached gravity from the perspective of quantum field theory. He asked, if every other fundamental force is mediated by particles, photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, then what mediates gravity? The theoretical answer, proposed but never observed, is the graviton, a massless spin-2 particle that would carry gravitational force between massive objects. Feynman worked extensively on trying to build a quantum theory of gravity using gravitons, and he ran into a catastrophic problem. When you try to apply the mathematical tools of quantum field theory to gravity, the calculations produce infinities. Not useful infinities that can be managed mathematically, but unmanageable divergences that make the theory completely unpredictive. Every other fundamental force has been successfully incorporated into the quantum framework. Quantum electrodynamics, QED, that we covered in our mirrors video, is extraordinarily precise. The strong force and weak force have been unified in the standard model of particle physics, but gravity, stubbornly, refuses to fit. Feynman, with characteristic honesty, said that gravity remains the most mysterious of the forces, precisely because it is simultaneously the most familiar and the least understood at the quantum level. We experience gravity every second of our lives. It is the force we have known the longest, and yet, at the deepest level of physical reality, we have no working quantum theory of it. General relativity and quantum mechanics, the two greatest theories in all of physics, are fundamentally incompatible with each other. They cannot both be completely correct. And nowhere is that incompatibility more stark than in the theory of gravity. Something, somewhere in our understanding, is wrong, and we do not yet know what. This brings us to what many physicists consider the single greatest unsolved problem in all of science, quantum gravity. How do you reconcile Einstein's general relativity, which describes gravity as the smooth, continuous curvature of spacetime, with quantum mechanics, which describes everything else in terms of discrete, probabilistic, quantized interactions? General relativity is a theory of the very large, planets, stars, galaxies, the large-scale structure of the universe. Quantum mechanics is a theory of the very small, atoms, electrons, photons, quarks. In most situations, you can use one or the other without needing both. But there are places in the universe where both are required simultaneously. Inside a black hole at the singularity, space-time curvature becomes infinite. You need quantum mechanics to understand what happens there. But quantum mechanics breaks down in the presence of infinite curvature. At the very beginning of the universe, the Big Bang, all the matter and energy in existence was compressed into a region smaller than a proton. Quantum effects and gravitational effects were inseparable. Without quantum gravity, we cannot understand the birth of the universe. Physicists have proposed several approaches to quantum gravity. String theory suggests that all fundamental particles, including the graviton, are actually tiny vibrating strings of energy. Different vibrational modes of the same fundamental string produce different particles. It is mathematically extraordinarily rich, but it has not yet produced testable predictions that distinguish it from other theories. Loop quantum gravity proposes that space-time itself is quantized, that there is a smallest possible unit of space and time, that the fabric of the universe is not smooth but made of discrete loops at the Planck scale, about 10 to the power of negative 35 meters. Both approaches are works in progress. Neither has been confirmed experimentally. We are, right now, in the middle of one of the greatest unsolved problems in human intellectual history. And that is not a failure. That is a frontier, the most exciting place in all of physics to be. Let us bring gravity back to the personal for a moment, because I think the most powerful thing about understanding gravity at this level is what it reveals about your own place in the universe. Right now, your body is generating a gravitational field. Every atom of mass in your body curves the space-time around it, infinitesimally, undetectably. But genuinely, you are gravitationally attracting every other massive object in the universe. The chair you are sitting on, the building around you, the moon, the sun, the Andromeda Galaxy 2.5 million light years away. The force is vanishingly small, but it is real. It is there. The equations are unambiguous. Every time someone has ever stood on Uluru, on the harbour bridge, on the peak of Mount Kosciuszko, they were slightly further from Earth's centre. Gravity was very slightly weaker. Their clocks ticked fractionally faster due to gravitational time dilation, not enough to notice, not enough to measure without extraordinarily precise instruments, but real. You have been experiencing gravitational time dilation every single time you climb a staircase. Going up, time moves fractionally faster for you. Coming down, fractionally slower. The universe applies these rules without exception, without favoritism, to every mass, everywhere, at every moment. The same gravitational waves that LIGO detected from two black holes a billion light years away passed through your body on the 14th of September 2015. They stretched and squeezed you by an amount so tiny it defies imagination. You were touched by a ripple from a billion-year-old collision, and you had no idea. Feynman told a story about his father. His father would take him for walks as a child and point to birds. And he would say, "Richie, do you see that bird?" In different countries, that bird has different names. In Portugal, they call it this. In China, they call it that. But knowing all those names does not tell you a single thing about the bird itself, about how it flies, about what it eats, about why it sings. Feynman applied that lesson to physics his entire life. Knowing that gravity follows an inverse square law, knowing that F equals mg, knowing that acceleration due to gravity at Earth's surface is 9.8 meters per second squared, that is knowing the names. Understanding what gravity is, why masses curve space-time, why there is no working quantum theory of gravity, what happens to space-time inside a black hole, that is the bird. We have extraordinarily good names for gravity. Newton gave us magnificent names. Einstein gave us even better ones. But the bird, the deep, true, physical nature of gravity, is still singing in a tree we have not yet climbed. And that, as Feynman would say, is not a reason for despair. It is a reason to keep walking. So let us bring it all together. Feynman style, Newton gave us a precise mathematical description of gravity and openly admitted he had no idea what gravity actually was. Einstein revealed that gravity is not a force, but the curvature of space-time caused by mass and energy. Objects in freefall follow the straightest possible path through curved space-time. Your weight right now is the normal force stopping you from following that natural path. Gravitational waves, ripples in the fabric of space-time, were predicted by Einstein and detected 100 years later, with Australian scientists and researchers playing a proud and significant role. And at the quantum level, gravity remains the great unsolved mystery, the one force that refuses to fit into our quantum framework, the frontier where general relativity and quantum mechanics collide, and neither survives intact. We know how gravity behaves. We know how to calculate it. We do not yet fully know what it is, and in that honest admission, there is more genuine scientific integrity and more genuine wonder than in any oversimplified answer your textbook ever offered. If this video gave you a deeper appreciation of the force you have lived with every second of your life, smash that subscribe button and join the Curious Physics AU family. New videos every week built for Australian students and curious minds. Drop a comment below. What blew your mind most? The equivalence principle, gravitational waves, the fact that quantum gravity is still unsolved? Tell me what landed. Share this with anyone studying HSC or VCE physics right now. This context will make everything in your gravity unit click in a completely new way. I will catch you in the next one.